In this video, we're actually going to start assigning electrons to orbitals for specific atoms. So for example, carbon, right? Carbon has an atomic number of 6, so it has 6 protons, right? 6 positive charges. If the atom itself is neutral, uncharged, then it also has 6 negative charges, so 6 electrons. And we want to know specifically where are those 6 electrons? What is their value for N? What is their value for L? What is their value for M sub L? Right? What specific orbitals are those electrons in? We are going to have some specific rules for doing that. The rules that we're going to follow is we're going to follow the Aufbau principle. And this rule tells us that we're always going to put electrons in lower energy orbitals before higher energy orbitals. And that's when we're forming its ground state. So our ground state, which is always what we want to do unless we're told otherwise, our electrons go into lower energy orbitals before higher energy orbitals. So remember, as our value for N gets bigger, the energy of that region of space, right, that orbital gets larger. So we're always going to put electrons in the first energy level before the second, before the third. So remember, N equal to 1 versus N equal to 2 versus 3 and so on. As I go in this direction, we're increasing in energy. We also have a trend with our subshells. Remember, s orbitals were spherical, right? So this was my nucleus, and we were using highlighter in the last video. So this here, right, is where my electrons are most likely to be if it is S-shaped. Just wanted to get rid of that line. So centered around the nucleus. Remember my p orbitals, these guys had 2 lobes and a node where that nucleus is. So the purple region, right, is where my electrons are most likely to be found. In a p orbital, they're actually not around the nucleus. And remember, electrons closer to the nucleus are lower in energy. So within the same shell, as my value for L gets bigger, the energy of that electron or the energy of that region of space also gets bigger, right? If I look at d orbitals, if I look at my cloverleaf one, I have 4 lobes, right? I have 4 regions of space distant from the nucleus where those electrons can be found. I have 2 nodal planes, so 2 places near the nucleus where I don't have electron density. So it gets even higher in energy. So within a shell, as L increases, energy also increases. And again, that's just because of the shape. Electrons closer to the nucleus are lower in energy. Electrons further from the nucleus are higher in energy. So if I have an S-shaped orbital, right, L is equal to 0, those electrons are centered around the nucleus. If I have a P-shaped orbital, L is equal to 1, those electrons are not centered around the nucleus, right? I have 2 lobes distant from the nucleus where those electrons can be. If I have a D orbital, L is equal to 2, now I have 4 lobes, 2 nodal planes, right? 4 areas distant from the nucleus where those electrons can be. So as I go from S to P to D, F, I would now have 8 lobes. My energy is also increasing. So as my value for N gets bigger, energy increases. And then within the same shells, within the same N, as my value for L increases, my energy is also increasing. So we're going to put it in the first shell before the second shell. We're going to put our electrons in an s orbital before the p orbital, right? This is the Aufbau principle. We're also going to follow Pauli exclusion. We already know this one. And when we're filling up our orbitals with electrons, this essentially tells us that we're going to have 2 of them maximum. So no more than 2 electrons max. It's kind of redundant, right? No more than 2 electrons max. We could just probably say no more than 2 electrons per orbital. Sorry for my horrible English there. And then we also know that they have to be spinning in opposite directions. So no more than 2 electrons per orbital, and they must have opposite spin. Right? If I go back up and look at this s orbital, right? And let's say this s orbital is in my first shell. So n is equal to 1, L is equal to 0, we already have that, M sub L is equal to 0. So if I wanted to put electrons in there, again, remember Pauli exclusion principle essentially tells us we can never have 2 electrons with all 4 quantum numbers the same. So if I try to put 2 electrons in here, they're going to have the same value for N because they're in the same shell. They're going to have the same value for L because they're in the same subshell. They're going to have the same value for M sub L because they're in the same orbital, which means my value for M sub S has to be different. So they have to have opposite spin. Since there's only 2 values for M sub S, I can only put 2 electrons max per orbital. I can have 1, I can have 0, but I can't have any more than 2. Otherwise, they would have the same number for M sub S also, and they would have all 4 quantum numbers the same. So electrons in lower energy orbitals before higher energy orbitals. When we do that, we're making the ground state. The excited state is when we don't follow the Aufbau principle. So when we put them in the higher, they actually can go up. Pauli exclusion principle, that one we already know. And then one more rule, Hund's rule. And Hund's rule says that when we have degenerate orbitals, and I'll define that word here in a minute. So when degenerate orbitals, which are orbitals that have the same energy, so when we have orbitals that have the same energy, that's what degenerate orbitals mean, we're going to place 1 electron per orbital before they are paired. So remember, we can have 2, we're just not going to until each degenerate orbital has 1 first. So if I have orbitals that have the same energy, I'm going to put 1 in each before I pair them. That's going to be Hund's rule. So again, the question is, which orbitals have the same energy? Well, if we go back up to energy, we're saying as our value for N goes up, right, our energy goes up. As our value for L goes up, my energy goes up. I don't have M sub L on that list, right? If I was to take a dumbbell, region of space, right, if I was to take my P-shaped orbital and I draw it on that axis, or I draw it on this axis, sorry, those are supposed to be similar in size. I know I'm not drawing my axes because I'm being lazy on you. Or remember, this one's coming in and out at us. They have the same size because they're the same value for N. They have the same shape because they have the same value for L. All I'm doing is taking them and orienting them in space differently. That's not going to change their energy. So all 3 of my p orbitals have the same energy. They would be degenerate. So I'm going to put 1 electron here, 1 electron here, 1 electron here, before I go back and stick another electron. So when I get to my p's, 1 in each of the 3. When I get to my d orbitals, right, when we have d orbitals, L is equal to 2, so M sub L is -2, -1, 0, 1, and 2. I have 5 orientations And all of those are going to be degenerate. These are all going to have the same energy. So the values for M sub L have the same energy. Right? Orbitals in the same subshell are going to have the same energy. So they're going to be degenerate. So one more thing I want to do, and this one's going to take a little bit longer, but we need to know these orbitals. And I'm going to give you a shortcut on the periodic table. You might already know it, but I do want us to be able to do it without using shortcuts. I want us to be able to know where these are coming from. So it's going to kind of be a summary of the last video. I know the last one was kind of long, but this is important. So I do want to take the time to make a table. So it's going to be the whole width of this. And we're going to do our shell number. So our values for N. So this is going to be my shell. Then we're going to have our values for L, right? That's my subshell. Then we're going to do our values for M sub L. We're going to have to make this one pretty wide because once I get to like my F orbitals, I'm going to have 7 things to write. So this is going to be a pretty big column. This is going to be, remember, my number of orbitals. Right? It's the number of orientations, but the number of orientations is my number of orbitals. Each orientation is a different orbital. So let's make this column pretty wide. Then we're going to do the number of electrons per subshell. Remember, there can be 2 per orbital. And then we'll do number of electrons per shell. We'll just kind of total them and check our math. Couple more things. Remember, L is going to be equal to 0 to n minus 1. M sub L is negative L to positive L. We could add on here number of orientations. Okay. So, and then I guess also we'll add energy. As we go in this direction, energy is going to increase. I do have to have a couple asterisks, which I will explain after we make our table. So energy in general is going to be increasing as we go down, meaning when we fill our orbitals, we're going to start at the top, fill our orbitals with the electrons, we're going to start at the top and go down with a couple little asterisks I'll put as we go. So our lowest energy is our first shell. In our first shell, L is only equal to 0, right? 1 minus 1 is 0, so 0 to 0 is just 0. And then we'll put the letter next to it, so S. Values for M sub L, right? Just 0. So that means I have 1 S orbital. Right? Negative 0 to positive 0 isn't a thing, so it's just 0. Since there's one orientation, since there's one s orbital, I can have 2 electrons, right, per. So that gives me 2 electrons. And that's it for the first shell, right? There's only one value for L, so only one set for M sub L, just 2 electrons, which means I only have 2 electrons possible in that first shell, right? My reason for that is that L is only equal to 0. M sub L is only equal to 0, so I only have one orientation. Pauli exclusion principle, I can only put 2 electrons in it. My second shell. When I get to my second shell, we now have 2 values for L. So L is equal to 0, and then it's also equal to 1, right? Because 2 minus 1 is 1. So L is 0 and 1. So this is my S, this is my P. When L is 0, M sub L is still 0, so I have 1 s orbital. When L is equal to 1, M sub L, negative 1, 0, positive 1. So we have 3 p orbitals. Maybe we should have made this column, instead of values for m sub L, actually do it the number of orbitals. I'm going to actually, you don't have to erase this part if you don't want to, but I'm just going to make that our main focus because it's going to get big. So let's do, sorry to change this on you. The part that's in parentheses isn't going to be in parentheses. If we want, we can add this in parentheses, but we're going to do the number of orbitals. The number of orbitals is going to be based on the number of orientations, which is based on our number of values. We're just going to run out of room, and then I think when we actually do our diagrams here in a minute, this is going to be the more useful way for the table. So I have 1, and then in parentheses, m sub L is 0. Here I have 1, m sub L is 0. Here I have 3. Those are all going to be degenerate. They're all going to have the same energy. Okay, sorry about that. So remember now, I can put 2 electrons per orbital. So 1 orbital, right, times 2 is going to give me 2 electrons. 3 orbitals times 2 is going to give me 6 electrons. So I have 3 different regions of space that all have the same energy with 2 electrons in each, is what that last one is saying. And then my total in the shell, 2 plus 6, is 8. I have 4 orbitals total, right? I have 1 s orbital and I have 3 p orbitals. So I have 4 total orbitals. 2 electrons per orbital gives me that 8. Just double checking that math a different way. Okay, third shell. In our third shell, L can be 1, it can be 2, and it can be 3. When it's 1, it's an S. When it's 2, it's a P. When it's 3, it's a D. M sub L is still just 0. M sub L is still -1, +1. So -1, 0, and +1. And then I actually have 5 values for this one. M sub L is -2, -1, 0, 1, and 2. So 5 orientations, 5 orbitals. All of them are degenerate. They all have the same energy, right? They're in the same shell, shell 3 right now. They're in the same subshell, L is equal to 2. So they have the same shape, the same distance from the nucleus, so they're going to have the same energy. So electrons, since I have 1 s, I can have 2 electrons in it. Since I have 3 p orbitals, and I can put 2 in each, that gives me 6. I have 5 d orbitals, I can put 2 electrons per, so that gives me 10. I have, if we want to do it this way, I have 9 total orbitals, right? They don't all have the same energy, but I have 9 total orbitals. So 9 times 2 would give me 18, and then we can do the math by adding these together. 2 plus 6 is 8 plus 10 is 18. So just double checking our numbers. I'm going to put an asterisk on those D's. So this D gets an asterisk. And that's just our energy. So I will, again, define those after. So 4. So L can be 0, 1, 2, and 3. So S's, P's, D's, and our first appearance of F. Asterisks, D still gets 1. And F actually gets 2 asterisks, double asterisks. Again, I will define those, I promise. So only 1 s orbital because m sub L is still just 0. 3 p orbitals because m sub L is still -1, 0, and 1. 5 d orbitals because m sub L is still -2, -1, 0, 1, and 2. 7 f orbitals, right? M sub L is equal to -3, -2, -1, 0, 1, 2, and 3. And if you were to count those numbers, right, how many numbers do I have? 1, 2, 3, 4, 5, 6, 7. So 7 ways I can orient an F-shaped region of space in space. So I have 7 orientations, I have 7 orbitals. All of them are degenerate. They all have the same energy. So following Hund's rule, I would put 1 into each of those before I ever put 2 in any of those. Electrons, since there's 1 orbital, I can have 2 electrons. 3 orbitals gives me 6, 5 orbitals gives me 10, and then 7 times 2, and this is maximum, of course, I can have 14. We should maybe add that up here, max. We can have less, but that's going to be my maximum. Total. So 2 plus 6 plus 10 is 18, plus 14 more gives me 32. If we go and count it the other way, I have 1 plus 3, so that's 4 orbitals, plus 5 is 9 orbitals, plus 7 gives me 16 total orbitals. Again, not all of them have the same energy, right? The different subshells, the different values for L have different energies. But I do have 16 regions of space in my 4th shell, right? My 4th energy level. 16 times 2 is 32. So those numbers are working. And then I'm not going to do a full 5, but just so you can kind of see what we're doing, right? If I was in my 5th energy level, 0, 1, 2, 3, and then I guess 4 is mathematically possible. I had said before that we don't actually have any atoms that we know of right now that actually have electrons in the G subshell, but it's possible, right? Mathematically, that does exist. 1 orientation, 3 orientations, 5 and 7. I'm sure you guys are seeing the pattern without working it out. How many different ways would there be to orient a G-shaped region of space? Yeah, good, 9. M sub L would be -4, -3, -2, -1, 0, 1, 2, 3, and 4, which would be 9 values. I'd be able to put 18 electrons total in that G subshell because I have 9 orbitals. Again, I'm just going to cross it back off now that we put it on there. Because we don't have, right, what we're trying to do here is put electrons in atoms that we know of into orbitals. I'm not going to occupy that region of space. It'll always be empty, so we can just leave it off. If we want to put our asterisks on here, these are going to be important. 1, our F's are always going to get 2. We would actually put 3 on our G's, but we're not going to include G's. Okay. So kind of what we're doing here. I'm going to, whenever we designate an orbital, we're going to designate our number for our shell, and then we're going to designate our letter for our subshell. So I'm going to have a 1s orbital. That's going to be my lowest in energy. I have 1 of them, so I can have 2 electrons total. Following off-ball principle, my next highest, 2s, I have 1 of those. I can put 2 electrons in it. Next, I'm going to have 2p. There's 3 of those, which means I can have 6 electrons in it. Then 3s, then 3p, then 3d, but there's an asterisk, so oops, what's going on? Let's go to find that. Remember the shape of those d orbitals? Right? Those d orbitals had those 4 lobes distant from the nucleus. Because of that shape, the energy of the d orbital of a specific shell is actually higher in energy than the s orbital of the next shell. I will write that down. But if we go back up and look kind of what I just said, let's erase some of this highlighter here. Oop, I just wanted the highlighter to go away. So this d orbital that I have this asterisk on, because of the fact that I have 4 regions of space in that region of space, right? 4 lobes distant from the nucleus. This 3d orbital is actually higher in energy than this 4s. Because remember, s's are spherical and those electrons are centered around the nucleus. So that is our reason for it. It has to do with that shape again. So let's write that. So the d, we could just say orbitals instead of subshells if we want. The d orbitals of a given shell are higher in energy than the s orbital of the next shell. S orbital, it's not plural, remember there's only one of them. D orbitals, there's 5 of them, so plural. So the d orbitals of a given shell are higher in energy than the s orbitals of the next shell. So when we're going in order, I'm going back up to my very first one here. I'm going to have 1, right, 1s, then 2s, then 2p, right? We're increasing in energy. 3s, 3p, then I'm actually going to go and do 4s, then I'm going to go back up and do 3d. And again, that has to do with the shape. I do want you to know that. Let's see if I can erase stuff with a finer eraser. I'm going to want to circle stuff again, so I just want to get this out of here. Okay. Double asterisk on the F. The F orbitals of a given shell are higher in energy. Remember, these guys have 8 lobes, right? So 8 places distant from the nucleus where those electrons can be. So the F orbitals of a given shell are higher in energy than the, we can word this a couple different ways. Let's say then the d orbitals of the next shell. It might be easier to think about it higher in energy than the s orbitals of 2 shells higher. I am going to give you a shortcut on the periodic table, and this last one's kind of that the F orbitals is easier to remember. I guess they're all easier to remember on the periodic table, but it's going to be helpful once you have the periodic table to be able to make clear on that one. But if we go back up, instead of starting from the very beginning, let's just start with the 3. So I'm going to have 3s, then 3p. I get to this asterisk, so I have to go and do 4s. Then we're going to go back up and do 3d. I've already done 4s, so 4p. I'm now to a d again, so I'm going to do 5s. I'm going to go back up and do 4d. I promise we will write all of this down. Now I'm at this double asterisk, so I have to go down and do 6s before I go back up and do that 4p. So 4 and 6, 2 shells higher. That's making sense. Let me actually put that 6 on there because we're going to need it when we do it. I'm just going to get rid of this and make it part of my table. Give you guys a chance to breathe here while I remake my table. So let's get rid of this G, because we're not going to use it. It does exist there. Don't think it doesn't. We're just not going to use it. So 6, 0, 1, 2. We're not going to actually use 2 neither. Actually, we will, sorry. So S, P and D. Okay. So let's do an example. We'll start with carbon. That was the one we started the chapter with. So carbon has an atomic number of 6, so 6 protons, which means if it's uncharged, it also has 6 electrons. So what we're going to do is we're going to draw orbital diagrams. And I do them differently than the text, and I'll show you how the text does it. I want you to do it the way that I'm doing it. It's more descriptive, and I'll show you the difference, and you'll see. But we're going to do orbital filling diagrams. So what we're going to do is a line is going to represent an orbital. So for every orbital I have, I'm just going to draw a line. The book is using a square. If you want to use a square still, you can. It's just that's annoying. It's a lot faster to draw lines than it is to draw squares. And we're going to put electrons in them, and it just gets messy. So the book is using a square. If you want to do a square, you still can. I'm going to use a line. So a line is going to represent an orbital. An arrow pointing in one direction is going to represent an electron. An arrow pointing in the opposite direction is going to be an electron spinning in the opposite direction. So remember, I can only have 2 electrons per orbital, and they have to be spinning in opposite directions. So each line can only have 2 electrons maximum, and they have to be pointing in opposite directions. So that's my 2 electrons in an orbital. If I was to go and put a third one on there, now I'm violating the Pauli exclusion principle, and I also have 2 things that are going to repel each other. So maximum 2 electrons. Again, if you want to use the squares, you can. It's just takes a lot more. It's annoying. I would highly recommend drawing lines. Okay. The other thing is, and this is the big difference, the square and line is a minor difference. The big difference for us is I'm going to have energy increasing as we go up. So energy is going to increase this way. The book has energy increasing left to right, and I'll show you how that's problematic. We're not going to do it this way. We're going to use energy going up. So I'm going to put a line through this just so you have it. Once I do one, I'll show you the difference, and you'll see why energy going up is actually preferred. And it's not just me, most texts do it up. It actually saves space for typing in a textbook when you go in the other direction, which is, I think, why they do it. But it's not as accurate as going up. So carbon. I have 6 electrons. We want to know where those are. So I need to have 6 arrows because I have 6 electrons. We're going to follow the Orbital principle, so I'm always going to put them in lower energy orbitals first. We're going to follow Pauli exclusion principle, so I'm going to have only 2 maximum per line, right, per orbital, and my arrows have to be going in opposite directions. And then when I get to my P's, 1 in each of the 3 before I double them up. So going back up to the list, it's kind of nice if I could have both of these up at the same time. But my very first one, let's use a different color. Let's use green. So again, energy is increasing as I go down. I want the lowest energy. So 1s. So whenever we state our orbital, again, always our shell number and our subshell letter. And then I'm going to draw one line because there's one orbital. Remember, the lines represent the number of orbitals. So going back down, and remember, energy is going up, so I need to start down here somewhere. So 1s, and then one line because there's one orbital. Going back up to our table, my next one, 2s, and again, I'm going to draw one line because there's one orbital. And let's actually do the next one. We're here. After 2s, I'm going to have 2p, and then I'm going to draw 3 lines because there's 3 orbitals. And they have the same energy, so I'm going to draw them right next to each other. I'm not going to draw them higher, right? They're degenerate. All my values for m sub l have the same energy. So we said that we had a 2s, we're going to draw one line, and then 2p, and I'm going to draw 3 lines, and I'm going to draw them right next to each other. This is where the book directions get kind of screwy. So they're doing 1s, then they're doing 2s, and then they're doing 2p, and then they're drawing the 3 lines, but they're saying energy is increasing in this direction. And when you do that, that would imply that this orbital is higher in energy than this orbital, and that orbital is higher in energy than this orbital, and they're not, they're the same. So energy going in this direction doesn't work for degenerate orbitals, right? Those have the same energy. By us going up, I can draw them at the same level, and then I'm showing them with the same energy, and that's why I want us to do it this way. So please, energy up, ones that are degenerate, have them on the same. So that's enough. If I wanted the next one, if we go back up, I don't need one for carbon because I only have 6 electrons. But if we were to add, right, I'm going to draw 3s next. I'm going to draw 1 line because there's 1 of them. Then I'm going to draw 3p. I'm going to draw 3 lines because there's 3 of them. All of them next to each other because they have the same energy. We will do one where we have to use more, so that's why I'm going to erase that. Okay, let's put some electrons in. So I have 6 electrons. Sorry, to back up here. So 6 arrows. We start at the lower energy one. 2 max, opposite spin. So that's 1, 2, 3, 4. Now I have degenerate ones, so I have to put 1 in each. So 5 and 6. I put them in the first 2 and I put them both up. You don't have to. All that matters is for those p orbitals is that you have 2 electrons. I guess 2 of the orbitals have 1 electron in each. So if I wanted, I could have put 1 here and have it going down. I could have put 1 here and have it go up. I could have put 1 here and 1 here. It doesn't matter. It only matters that there's 1 electron in 2 of those 3 orbitals. Since there's only 1 in each, it doesn't matter which way they're spinning because there's only 1 in each. I like to be systematic, as just me, so I usually do this. But by all means, do it however you want. As long as 2 of those 3 orbitals have 1 electron in each, you're going to be right. So this would be my orbital filling diagram for carbon. So I won't generally ask you to do this. It's just, I always make a big deal about how electrons, when we draw like our Bohr pictures, right? If I was to, right, what we normally do when we draw atoms, oh, that's big and fat, that's not what we wanted. Right, we normally put our nucleus in the middle and then we draw, right, we make them round. And I have said several times that that's not what atoms look like, right? So I want to draw a picture kind of what, and this is still not greatly accurate, but it's a little bit better. So I'm going to have my nucleus in the middle. It actually has 6 positive charges in it. And then I have an S-shaped region of space, and that has 2 electrons in it, if we wanted to put electrons in here. And they're following some sort of wave-like pattern. And then I have a bigger sphere. Oops, I want a highlighter. I have a bigger sphere. And it would be right over that one because it's centered. So another bigger sphere. I'm not going to go all the way over it because I want you to see the one that's underneath it. But it does go all the way over it. So bigger sphere. And then that has 2 electrons in it. And then I have a dumbbell, and that has 1 electron in it. And then I have another dumbbell, and that has 1 electron in it. So carbon. And of course not to scale at all. Remember that those electrons, if that was the size of my nucleus, are like in my neighbor's house, right? Totally not to scale. But I have a spherical shaped region of space with 2 negative charges. I have a bigger spherical shaped region of space with 2 electrons. I have 2 different dumbbell shaped regions of space with 1 electron in each. That's our carbon atom. Let's do one more example with an orbital filling diagram. So let's look at, I want to do something that has d orbitals. Let's do bromine. So bromine has an atomic number of 35, so 35 positive charges. If the atom itself is uncharged, I'm going to have 35 negative charges, so 35 electrons. So when I do my orbital filling diagram for bromine, I'm going to have 34 arrows. We're going to follow all of our rules. So Aufbau principle, lowest energy orbitals first before the higher ones. Exclusion principle, maximum of 2 electrons per orbital, opposite spin. And then when I get to degenerate orbitals, orbitals that have the same energy, 1 in each before I pair them. So going back up to our order, I'm just going to do the first couple because we've already done them. So I have a 1s, there's 1 of them. 2s, there's 1 of them. 2p, there's 3 of them. So let's go down. This one's going to get kind of big, so make sure you give yourself enough room. So 1s, 1 value for m sub l. 2s, 1 value for m sub l. 2p, 3 values for m sub l, 3 orbitals. So going back, and we'll do a couple so we don't have to scroll so much. So 3s is going to come next. There's going to be 1 of those. Then I'm going to do 3p, and there's going to be 3 of those. So 3s, 3p, and then this is where we have that asterisk, so be careful when I go back up. 3D, there's that asterisk on it, so we're going to actually go and do 4s next. There's going to be 1 of those. Then we're going to go back up and do our 3D. I'm going to draw 5 lines for that one. So 4s, then 3D, and 5 values for m sub l, 5 orientations, 5 orbitals, so 5 lines. When I fill up those orbitals, I'm going to put 1 in each of those 5 before I pair them. Back. Making you guys dizzy with all my scrolling. The next one, we've already, right, it's where we're not highlighted anymore. So 4, and then P, and then I'm gonna have 3 of those. And that's gonna be enough for bromine. If we needed to do more though, what would come next, because I get to that asterisk again, I would do 5s, then I would go back up and do 4D. So 4p, there's 3 of them. And this is, since we said it, we would do 5s next, and then we would do the 4d. 1, 2, 3, 4, 5. If it's d, there's always 5 orientations, right? 5 values. Okay, now we have to put some electrons in there. So bromine has 35 electrons, 35 arrows. I'm gonna start at the bottom and go up. So 1, 2, 3, 4. These ones 1 each, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, again 1 each, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. So this gets me my orbital filling diagram for bromine. This electron doesn't look like he's in its orbital. Guess it is a probability. So again, my orbital filling diagram for bromine. We are going to do electron configurations also, so just be careful that you give me what I'm asking for in the directions. Electron configurations are going to be slightly different, so just be careful. These are orbital filling diagrams. I don't want you to get the problem wrong because you're not giving me the right thing. So orbital filling. I think the word diagram usually helps. Again, the text is doing this, so just be careful. I do want us to go bottom up for our energy.